Kinematics. Objectives. By the end of this lesson, you should be able to define average rate of change, define instantaneous rate of change, relate position, velocity, and acceleration, describe horizontal vertical motion of an object along a straight line, give the conditions of an object speeding up or slowing down, and explain the difference between distance and displacement. So this lesson's all about moving on a straight line and how calculus relates to that. So we're going to talk about two types of movement: horizontal and linear motion. So if you're a particle and you're moving left and right, it'd be kind of like this. Right. The key thing is that your origin is 0, and moving right just means is positive. Moving left of the origin to be negative. That's all it is this orientation. When it's a vertical linear motion, you move up and down. So I'll draw this, but the general idea is if you go up, it's positive. You go down, it's negative. The ground equals 0. Most of the time we'll have like a projectile, so we kind of like this. But that's the two types of movements we're going to talk about. We're going to talk about moving left and right and moving up and down. Generally it's up and then falling. So, average rate of change. If you see the words average rate of change, or just average rate of change, that's the slope. That's all it is. It's just the slope. That's what average rate of change is, right? It's displacement over time with ellipse. If you look at all these formulas, that's the slope. Slope of a secant line is slope. So if I ever ask you to find the average rate of change, just find the slope. So again, cannot stress that enough. That's very different than instantaneous rate of change. Instantaneous rate of change is the derivative. So if you see that word right in front of it, the derivative. Right, if you look at these formulas here, they're the exact same formulas we use up here. What's the one difference? The limit, right? And the limit makes it calculus. So when we take the limit, it's a derivative. So if you hear the words instantaneous rate of change, you're just taking the derivative. Graphically, instantaneous rate of change is the slope of the tangent line, because that's what derivative is. But here's what's more important. Instantaneous rate of change, you should automatically know, oh, it's a derivative. But they might just say rate of change also. By default, we think rate of change, we think instantaneous rate of change, we think derivative. Only time we think of slope is if they say the word average. If they say average rate of change, then you're going, oh, it's slope. Instantaneous, or just rate of change, is a derivative. That's all it is, right? If you hear the words instantaneous rate of change or just rate of change, think derivative. Just take derivative, plug your values in. Instantaneous rate of change is derivative. Super important. So let's talk about what the main part is today. And the main part today is talking about what each derivative relates to in kinematics. So our original function is displacement. Displacement also known as position. So most of the time, this is our original function. This is our f of x. They'll actually use s of t most of the time, and we're going to be using t because we're talking about movement across time. So it has a time associated with it. So a lot of times we use s of t. And displacement is position. So the original function always can be, for most parts, maybe the position function. So if you ever see s of t, that's the displacement function. That just means, right, like we talked about earlier, how you move. So if I give something like this, 0 is the origin, this is where you start. Or it could be, if it's a projectile this way, 0 is the ground. Right? Going to the right is positive, going to the left is negative. That's all it is. Right? So the original function is position. If I ask you, what's the position at 1 second? Plug in 1. Let's say you get 13, right? All that means 13, usually like dimensions like meters or something. All that means is you're 13 meters right from the origin. You're over here somewhere at 13. That's all that means, right? It doesn't mean you're going, that's how fast you're going, anything. It's 13's position, so 13 meters right of the origin. If you got negative 13, you'd be 13 meters left of the origin. That's all that means. Right, 13 on this one would be 13 meters high, negative 13 meters in the ground. So just keep that in mind. When you're positive, you're to the right, negative to the left, and 0 is 0. So let's do a quick example of a couple problems that deal with this. The positional part given by the equation s of t. Notice again, s of t, it's position, or displacement. Same thing. Where t is measured in seconds and s is in meters. So they're saying this is meters, this is seconds. Right? Stuff you plug in seconds, stuff you get out to meters. Find the position of the particle at 1 second. Okay, well, they want me, right, it's talking about position, so I'm using this function. They want me to plug in 1. So s of 1 equals 1 cubed minus 6 times 1 plus 9 times 1. 1 minus 6 plus 9, negative 5 plus 9 is 14. 4. Negative 5 plus 9 is 4 meters. Right, so it's a positive 4. All that means is that we're 4 right of the origin. So origin is right here, so wherever you started at, and then you're 4 meters to the right. You're right there. So that's what it means in context. Oh, at 1 second you moved 4 meters to the right, or you're at 4 meters to the right. Find the time when the particle is at the origin. Notice we're looking for time. Right, that's what we want, so we're not going to plug in here, we're going to plug into here. Particle is at the origin, so we're going to say s of t equals 0, because that's what the origin is, 0. So you just set 0 equal to t cubed minus 6t squared plus 9t. You could factor out a t because they all have a t in common. You're going to get t squared minus 6t plus 9. That does factor. T minus 3, t minus 3. Split it, and you're going to get t equals 0 and 3. So the particles of the origin at 0 and 3 seconds. So at 0 seconds and at 3 seconds, it's at the origin. And units are kind of important when we're talking about this stuff here. It's all about position and particle movement. So that's displacement. So what comes out of displacement? Well, once you go below that, then we have two things. We have velocity and acceleration. Right? Velocity is kind of how fast you're going. We'll talk about a little more about that in detail. And then acceleration is how much you're increasing your speed or increasing your velocity. So we're going to talk about this more in detail, but the general idea is, right, when you take the derivative of displacement, you get velocity, right? So if you start with s of t, you take the derivative of that, you're going to get the velocity function. Take the derivative of that, and you get the acceleration function. Right? So the first derivative is velocity, the second derivative is acceleration. And this is a big thing to know. You have to keep this in mind because you have to know how to go up and down in these things. Another big thing to keep in mind is what is velocity, right? Velocity is like movement. It's a speed and a direction. It's how fast you're going generally. But don't forget, it also includes direction. Why is that important? Because what we're going to do a lot of in the first and second derivative is what we always do in first and second derivatives. We're going to make a sign chart. So let's say we make a sign chart for this thing. Let's just have point A. We'll have like plus and minus. So with this, if we're talking about velocity, what does the minus mean? It doesn't mean you're decreasing velocity, not at all. What it means is you're going to the left. Just like a position, this means your velocity is moving to the left. It says moving. Left. That's all that is. I can't even read that. To the left. Moving. Right? If you get a positive, this means your velocity moves to the right. That's all that means. There's no increase and decrease in velocity right now. It's just saying you get a positive move to the right, negative move to the left. So that's important to keep in mind. Also, it's very important to keep in mind, when you set equal to 0, that means you're not moving. That's highlighting. Velocity of t equals 0 means not moving. It's at rest, or it's not moving, or stabilized, or reversing direction. All the things that mean the same thing, not moving. So you're stopped at velocity. When your car stopped or whatever, your velocity is 0. Okay, let's do a couple examples that deal just with that. So find position of the particle given. So notice how they give us the position function. And what they want us to do is find the velocity. Well, that's the first derivative. So take the derivative of that. And I guess in this case I should say s of t. So s prime of t, also known as velocity function. It's just the derivative of that, which is 3t squared minus 12t plus 9. What is the velocity at 2 seconds? Now again, notice how they give us time. So I'm plugging in for my t's. 3, 2 squared. By the way, it should be meters per second. Every time you take a derivative, you can divide it by seconds because you're taking with respect to time, so you're dividing by time every single time. So 2 squared minus 12 times 2 plus 9. This goes first. So 9 times 3 is 27. 27 minus 9 is 18. 18 minus 24 is a negative 6. So you're moving to the left. Meters per second. You're moving to the left at 1 second. So your particle is just moving to the left. When the particle at rest? At rest means your velocity is 0. You're not moving. Right? That's the key thing about this chapter, this section, is understanding like the key vocab words. It's at rest, that means it's not moving, velocity 0. So you can set your equation equals 0, and then solve it. To save you guys time, I'm not going to solve that, but that's all you do. Just go in there and solve it, get your times when it's at rest. With the particle moving in a positive direction, this is a sign chart. So, how do we get a sign chart? Well, we set the derivative equals 0 like we always do, which we just did right here. Probably should have solved it now. Let's see. Divide everything by 3, so that's going to be t squared minus 4t plus 3. I'm going to get t minus 3, t plus minus 1. So t equals 1 and 3. So we've done that earlier. So we're going to set the derivative equals 0. And then, like as I just showed you, if you set the derivative equals 0, you're going to get this, which you can factor and solve and get t is going to equal 1 and 3. Which, by the way, something we haven't talked about this yet. Since we're doing time is always positive. It could also be 0, but time is always positive. You can have a negative time. I'm never going to ask you what's the velocity at negative 3 seconds. It doesn't make sense. So in this case, our domain is always going to be 0 to like infinity, because we're dealing with time. So I get 1, 3. I make a sign chart. 1, 3. Right, plug your test points into the derivative, plug into here. That's the derivative. And I'll tell you right now, you're going to get plus, minus, plus. Right, and what does it tell me? Which move in the positive direction? The positive ones. Negative infinity to 1, union 5 to infinity. And that's how velocity is done. Next up, acceleration, right? So we talked about this, right? It goes from position to velocity with a derivative, and then another derivative is acceleration. Right, so acceleration is how much velocity is increasing. This thing like a car. Right, if you're going forward and you press on the acceleration, the gas, you can go faster. Right, so that's what acceleration is. It's how fast are you increasing your speed. And again, if I ever say average acceleration, you're just saying the slope. So some key terms right here, right? If acceleration is positive, the velocity is increasing. If it's negative, velocity is decreasing because you're decelerating basically. You're going to the left. And velocity may be max or min. So this is the thing we're going to talk about more in a second. Anytime I ask you to find the max of min of something, it's always the same thing. You set the derivative equal to 0. That's how you find the max and min of almost anything. Right? If I want to find the max position, you take the derivative of that, which is velocity, set equal to 0. In this case, if you want to find the max velocity, take a derivative of velocity, get acceleration, set equal to 0. Heck, if I want to find the max acceleration, take the derivative of that, set equal to 0. That's how you find the max of stuff. So you just got to understand when I say acceleration, though, it's all about increasing velocity. If they talk about increasing velocity or decreasing velocity, you're talking about acceleration. So let's do some acceleration problems. So same idea. Like here's my position function, same one we've been working the whole time. So we took the first derivative last time. We got 3t squared minus 12t plus 9. I want acceleration, so I'm going to take another derivative. So I'm going to get 6t minus 12. Second derivative is always so much nicer. When is the acceleration positive, right? Again, they're asking me if it's positive or negative. That's a sign chart. So we'll do another sign chart. Now it's time for the second derivative. So this thing equal to 0. I'm going to get 0 equals 6t minus 12. At 12, t is going to equal 2. Now, that's not my answer. It says, when is the acceleration positive? But let me know what my critical point is. That's what I was doing. I was finding a critical point. All right, so let's find you set that derivative equal to 0. Find a critical point. In this case, possible inflection points. Then we do a sign chart. It's like 3, plug into your derivative. That's 18 minus 12, so that's a positive. On the other side, plug 1. That's 6 minus 12 is negative 1. So acceleration is positive between 2 and 2 and infinity. That's acceleration. So those are 3 main functions we're talking about. Right, so let's review a little quick, right? So remember, position function is generally your starting function. Again, sometimes it might start your velocity, and you just gotta watch out. Because they start you at velocity and they ask you for acceleration, you just gotta take one derivative. If they start you at velocity and once you find a position, you have to go backwards, which we'll do next semester. So position function is the original one, right? The velocity function is the first derivative. And it's like everything else, you gotta understand what velocity tells you, right? Position tells you, let's look at a sign chart for position function, right? If you get a positive, that means you're right of the origin. If you get a negative, you're left of the origin. But position, like where you're at. Velocity, if you do a sign chart, the thing about velocity means it's movement. It's how fast you're going for the most part, right? So your velocity is moving right, your velocity is moving left if you do a sign chart, right? So moving left, moving right. That's what velocity is, right? It's about moving. Right, where position is where you're at. The acceleration is the second derivative, right? If you do a sign chart for acceleration, this means your positive means your velocity. Someone wants a little different. Velocity is increasing. Minus means your velocity is decreasing. Now this isn't speeds increasing or decreasing. That's a different matter. Is your velocity increasing or decreasing? Are you going right or are you going left? Is that going at a faster rate? So that's the general concepts. Here's a useful table, because the big thing with this lesson is all about like vocab. Understand what you're talking about. So if I say like, what's the initial conditions? Initial conditions just means time equals 0. Like what's your position when you first start? What's your velocity at the start? What's your acceleration at the start? You just plug in 0 for everything. So initial conditions is always 0. If they say at the origin or at the ground, right, depending on the talk, that's a place. It's where you're at. So you're gonna set the displacement or the position to 0. Right? At the origin, on the ground, those are positions. So you set the position equals 0. Stationary means you're not moving. You're at rest. Well, what has to do with movement? Velocity. If you're not moving, your velocity is 0. If you reverse direction, it's a little funky. You have to stop to reverse direction. That's why the velocity is 0 again. So if you want to go from right to moving to left, you got to stop for a split second. Max or min. So notice it says maximum displacement, right? Like I said earlier, the way you do max or min of anything is you take the derivative set equal to 0. Right? Again, so if you're trying to find the max velocity, take the derivative velocity set equals 0. Max acceleration, take the derivative acceleration set equals 0. That's how you find the maximum of anything. Let's not forget units. In IB, they like to use this notation. So most of the time, the original S of T would just be in meters or feet or something. Velocity, you divide by time, so divide by seconds. So IB does this weird ms to -1 power. It's just a fancy way of writing this. Meters over a second. Same thing here. If you had acceleration, you took another derivative, so you divide by one more time. Right here would be meters over seconds squared. So that's the units. So we want to speed. I know what you're thinking. That's this velocity. It's not, right? Velocity has a direction, right? Very important. Velocity has a direction, right? It tells you right or left. So in velocity, you say you're going -20 miles per hour. It means you're going to the left side 20 miles per hour. Speed doesn't give a crap about that. Speed sees this absolute value velocity, right? Speed's always positive. That's all it is. So just keep that in mind. Speed is always positive. This is the absolute value velocity. So you find velocity, take the absolute value of that. You got speed. So this is how fast you're going. So next step, how do we know if speed's increasing or decreasing? That's a little funky. Speed's increasing when the two forces are working with each other. So if you have velocity and acceleration and they're both positive, that means you're going faster to the right? Velocity is going to the right, your acceleration is increasing the velocity, it's making the velocity positive, which is going to the right. So you're getting faster. Velocity and acceleration are both negative, same idea. You're just getting faster to the left side, right? Left doesn't mean decreasing speed. It doesn't mean you're going negative 20 miles per hour. It means you're going to the left 20 miles per hour. So if you want speed to increase, they have to both be the same sign. So I don't know what that, look, you're not the only one that doesn't know what that says. I cannot read that at all. So speed increasing. You want the same sign, because that way they work together. Likewise, if you want speed to slow down, speed decreasing, this is decreasing. They have to be working against each other. Velocity wants to go right, accelerator wants to go left, or vice versa. Right? This is when speed slows down. It's like putting on the brakes, right? You're going forward, like 13 miles per hour, or whatever. Hit the brakes are making you pulling you the opposite direction, so they slow down. So opposite signs. So again, opposite signs is decreasing. Same signs increasing. So those are all the gist of stuff. Let's do a few examples, like the laid out examples. Our first full example right here. Let x of t, that's its displacement. They're using x, it's fine. Equal t cubed minus 3 halves t squared minus 18t plus 30 represents the position of particle traveling along x-axis where t is given in seconds and x is given in inches. Right, so we're using inches and seconds. So find the position of particle at 1 second. This is how we did before. Just plug in 1 into our position function, which is x of t. Right, in this case, x of t is our position function. Take derivative of that velocity, derivative to make acceleration to v. That looks worse. To v. So if I put this particle at t equals 1 second, this is plug in 1 for our function. So 1 cubed minus 3 halves minus 18 plus 30. That kind of sucks. 12 plus 1, 13. 13 minus 3 halves. So 11.5 is what I get. About 11.5 inches. Right, so the position at 1 second is about 11.5 inches to the right of the origin. That's what that means. You're just to the right of the origin. Wherever you started, you're now at 11.5 inches away. Find the velocity. That's the first derivative, so take derivative of this. So the velocity function, or x prime of t, I have vt here. Take derivative, you get 3t squared. Bring down the 2, that goes away. Minus 3t minus 18. So that's my velocity function. This will be meters per second. Or, sorry, inches per second. What is the velocity after 2 seconds? Well, we have velocity function, just plug it in. Velocity of 2 is 3 times 2 squared minus 3 times 2 minus 18. Do that first. 4 times 3 is 12 minus 6 minus 18. So negative 12 meters per second. So at 2 seconds, you're moving to the left at negative 12 miles per inches per second. Right, this means you're going this way. You're moving that way at 2 seconds. With the particle at rest, so we're going to set the derivative equal to 0. Particle at rest, it's not moving. You set velocity equal to 0. So we have our velocity equation, 3t squared minus 3t minus 18. Right, we could set equal to 0 because we want to rest, and then we could solve this. I might need it later, so like last time, let's divide everything by 3. T squared minus 1x, minus 6 is equal to 0. It's actually not that hard to solve. X minus 3x plus 2 is equal to 0. X equals negative 3, and negative 2. But again, remember, we're doing time. Negative 2 makes no sense. Our domain for all this stuff is going to be times greater than 0. So that is not an answer. At 3 seconds, the particle is at rest. When is the particle moving to the positive direction? Right? It talked about movement, so it's a sign chart again. So now when I do a sign chart, since we talked about before, we have to start at 0. So we start at 0. I'm going to go to 3. And that's all I need. Right? We have our critical point, and we start at 0. That's all. So what we do next is some text points, like let's say 1, plug it into the derivative, plug it into the derivative right here. I'm going to get 1 squared minus 1 minus 6. That's going to be a negative. Plug in 4. I get 16 minus 4 minus 6. Close with no cigar. That's a positive. So when we're moving in the positive direction, 3 to infinity. Find acceleration at the time t, right? Acceleration is the next derivative. So acceleration is let's take a derivative of our function up there, 3t squared minus 3x minus 18. That was the first derivative. Now we're on the second one. So take derivative one more time. 6t minus 3 equals 0. Right? That's my acceleration across time. So inches per second squared. When's acceleration positive? So again, that's from positive negative. That's a sign chart. So let's find our critical points. I get t equals 1/2. So we have one critical point. We start at 0. We have one critical point at 1/2. Right? Pick a test point, plug into the derivative. So let's say I plug 1/4. 1/4 times 6 is 1.5. That's me a negative. 1.5 minus 3 is a negative. And then pick something here, a lot easier, like 1. I get 6 minus 3 is a positive. Excel's positive over here. 1/2 to infinity. 1/2 to infinity. Is the speed of the particle increasing or decreasing when t equals 2 seconds? So this one's a little tricky. Remember, speed is this absolute value of velocity. That's all it is. So this, we found the velocity here. No, we didn't. But if we found the velocity, just make it positive. That's your speed. How does this work though? With the speed of the particle increasing or decreasing when t equals 2 seconds? Now remember, increasing and decreasing has to do with the velocity and acceleration. If they're the same sign, you increase. If you're different signs, anywhere, you decrease. So one easy way to do this is actually just to plug this into both velocity and acceleration. If you get the same sign, they're increasing. If you got different signs, then decreasing. Right? So let's try velocity of 2. That was, look, my formula up there. My velocity at 2, my formula is 3t squared minus 3x minus 18. Plug the 2 in, I get 4 times 3 is 12, minus 6, plus 8. Plus 18, makes it a little bit tougher. And I get 6 plus 18 is 24. So this is a positive. Let's check acceleration. If we get the same sign, then it's increasing. If we get different signs, it's decreasing. The acceleration formula is this. Plug in the 2. 12 minus 3 is 9. So this is also positive. So speed is increasing. At t equals 2 seconds. Very important. It's not always just at 2 seconds, speed's increasing. Let's do another one. Let's look at this example. So first of all, GDC just means graphing calculator, or GDC graphical display calculator. If a stone is thrown vertically upward from the surface of an unknown planet, its height in meters after t seconds is given by this. So this is the height. So this is all, again, that's your original function. That's your displacement or your position. Only difference now is we're going upwards. Like you can see as a picture of the graph here, right? It's going to go up and then come back and fall. What's the velocity after 1 second? So again, notice velocity. So I'm going to take a derivative. So v of t, or h prime, is take a derivative of that. So 10 minus t. Then we're going to plug in 1. So velocity at 1 second is 10 minus 1, or 9 meters per second. Yeah, this is in meters. M. So the velocity after 1 second is 9 meters per second. So after 1 second, it's going that fast. What is the velocity of the stone after it has risen 18 meters? So look at this problem. This is a complex part of the problem right here. So risen 18 meters, that's a position thing. They're saying the position, h of t in this case, equals 18 meters. So I got to solve that first. I got to go 18 equals 10t minus 0.5 t squared. Now, there's a couple ways to solve this. You could try to set equal to 0 and then factor and complete the square. Factor or quadratic formula. But we could use a calculator, the GC, right? So the easiest way to do this is do y1, y2. Graph it, fix your window, and find the answer. For the sake of time, I'm just going to use this picture here. 18 would be around there, right? So it looks something like that. This would be, let's say this is 2, and let's say this is 18, just for the sake of it. Let's say 2 and 18 is the time, right? Now, keep in mind, I haven't answered the question yet. The question is what is the velocity of the stone, right? I'm looking for velocity. All I did here was go, okay, I have position. I could use that to find the time. So my time is at 2 and 18. So at 2 seconds and at 18 seconds, it's at 18 feet. And risen 18 feet. So actually, let's go down. I don't count that one, right? It's only risen, so this part. So all I gotta do now is plug in 2 to my velocity and get my answer. So my velocity is 10 minus t. So 10 minus 2, or 8 meters per second. So it's going 8 meters per second at when it has risen 18 feet. When does the ball hit the ground? So ground, again, notice how it hit the ground. That's position. We're not talking about how fast it's going or anything. It's come out, where is it at when it hits the ground? Well, as we talked about, the ground is 0. Right there. So how do we solve this? We set the original function equal to 0. Since it's equal to 0, we could just factor. So they both have you could factor out a t from both of them. Splitting a little early, sorry. Equals 0, then you split it. T equals 0, which we already know. That's not the one. Starts at 0. 0.5 t equals 0. Solve it. 10 equals 0.5 t. Divide by 0.5, you get 10 equals 20. When you divide by half, you just multiply that by 2. What is the speed of the ball when it hits the ground? So again, speed is the absolute value of velocity. Right? Velocity is speed plus direction. So if we just want speed, just drop the direction, just drop the sign. So velocity, we know our velocity equation from above was, what's our velocity equation? 10 minus t. So our velocity is 10 minus t. And I want it at 20 seconds. So absolute value of 10 minus 20, or negative 10, which is 10 meters per second. So again, at 20 seconds, it was going negative, it was going down 10 meters per second, but we just want the speed. So drop the sign. Speed doesn't care about sign. And it's going 10 meters per second when it hits the ground. Okay, one final example. Just making sure it's one final example. The position of a particle is given by the equation s of t equals t cubed minus 6t squared plus 9t, where t is measured in seconds and s is in meters. So again, this is in meters. Right, that's what m is. I should say this, right? M is in meters, time is in seconds. It's more the same thing, right? The key to this whole section is understanding like the vocab. If I'm talking about position, where you are at a certain place, it's position, original function. If I'm talking about how fast you're going, that's velocity. If I'm talking about how much you're increasing your speed, that's acceleration. That's the second derivative. That's all it is. If I want to know where your acceleration is positive, then you do a sign chart for the second derivative. I want to show you when your velocity is moving to the left. Do a sign chart for the second derivative, for the first derivative. That's all this is. So look at this one. What is the velocity after 2 seconds after 4 seconds? So, well, I got my displacement, so let's find the velocity. Take the derivative. 3t squared minus 12t plus 9. Right? And then velocity at 2 seconds is plug in 2 seconds. Plug in 4 seconds. I won't waste your time, but that's all you do. When's the particle at rest? Now again, we're talking about movement here. When are you not moving? So that means the velocity equals 0. Right? I'm not plugging in 0, I'm setting equal to 0. So 0 equals 3t squared minus 12t plus 9. I'm actually gonna solve this because I need it for the next one. So I'll divide everything by 3, and I get t squared minus 4t plus 3. Factor that, t minus 3, t minus 1, and I get t equals 1 and 3. So that's when you're not moving at 1 and 3. It's moving, and stops at 1 second, and moves again, stops at 3 seconds. When's the particle moving forward? So it wants to know when the particle is positive. So to do this, again, moving, that's the first derivative. We're going to do a sign chart. Luckily, we just found our zeros, 1 and 3. Now don't forget, it's an application, it's kinematics, so we always start at 0. Time is always positive in kinematics, or at least non-negative, I should say. So 1 and 3. Right? You put a little test point before 1, like 1/2, plug into the derivative. So plug in 1/2, I get negative, and I get another negative. A negative times a negative is a positive. Plug in 2, I get a negative, and I get a positive, so that's a negative. Plug in something like 4. So I circle these things, by the way, so I keep myself straight. I get positive, positive. So when is it moving forward? Looks like from 0 to 1. And 3 to infinity. So it's moving forward. Is the particle speeding up or slowing down at 2 seconds? So this one's a little tricky, right? I wonder if it's speeding up or slowing down. Remember, speeding up is when both the same sign. Velocity and acceleration are both positive, or velocity and acceleration are both negative. That's speeding up. They're working together. Slowing down, I don't know what I was trying to spell there. Slowing down is when they're working against each other. So plus or minus plus. If they're working against each other, slowing down, working with each other, speeding up. And the easiest way to do this at 2 seconds. So there's always 2 ways to do this. One way you could do the sign chart for each one and kind of compare them. But the easiest way to do this, especially if we're talking about a specific time, is just plug that into both of them. Let's find the velocity at 2 seconds. Now I wish I would have done it up here, but whatever, we move on. So let's plug it in. Right, I do this first always, so 4, so 12 minus 24 plus 9, negative 12 plus 9 is negative 3. Right, this is negative 12 plus 9, okay, yeah. So that's velocity at 2 seconds. It's moving to the left. Remember, that doesn't mean it's decreasing, it just means it's moving to the left for velocity. Let's see the acceleration at 2 seconds. So actually, we haven't found the acceleration formula yet, but let's do it right now, right? So it's the next derivative, so there's velocity. Acceleration will be the next one, 6t minus 12. So right here we're going to have 6 times 2 minus 12, which gets us 0. Now what does that mean? Well, first let's talk about what 0 means for acceleration, right? Just think about like you're driving. If your acceleration is 0, that means you're coasting. You're just at a constant speed. Right? So the general idea I said, right, they're working against each other. If they're working with each other, you're speeding up. If you're working against each other, you're slowing down. This is a negative 3 for velocity. Acceleration is 0. 0 is neutral. It's not positive or negative. So you're not speeding up or slowing down. You're coasting. Acceleration is 0. You're just keeping the same consistent speed. So is it speeding up or slowing down? It's kind of a trick question. It's doing neither. It's maintaining constant speed. Maintaining constant speed. It's coasting right now. So it's doing neither of those. It's not slowing or slowing down. And that's the lesson.